Question 10. The diagram shows a bar magnet and a conducting coil moving with velocities as shown below. Use Faraday's law to explain whether a current is induced in the conducting coil. So here you have four different cases where the coil and the magnet are moving with certain velocities, and we have to discuss in each of these cases whether there will be an induced current or not. Now Faraday's law states that whenever there is a change in magnetic flux through a coil, a current or EMF is induced in the coil. And what is important to note that there must be a change in the flux. It doesn't just relate to the presence of magnetic field. There must be a change in the magnetic flux in order for there to be an induced EMF. Now, one of the ways in which there can be a change in magnetic flux is when there is a relative motion between the coil and the magnet. When I say relative motion, that means either the magnet could be moving or the coil could be moving, or both can be moving with respect to each other, but there must be a change in position between them. That means if I have object A and I have object B, it doesn't matter who is moving or if both of them are moving, as long as either they are coming close to each other or going far from each other, as long as there is a change in distance between them, there is a relative motion and hence there will be an induced EMF. And one of the way to determine if there is relative motion between two objects is by looking at their relative velocity, which we call as delta V. As long as delta V is not equal to 0, the coil and magnet will always be in relative motion to each other. It doesn't matter whether this value of delta V is positive or negative. If it is not 0, that means they are either moving close to each other or they are moving away from each other. There will be a change in position between them. So we can say that there is an induced current between the coil and the magnet as long as the relative velocity value is not 0. Now, if the value of relative velocity delta V becomes equal to 0, this means that the coil and the magnet could still be moving, but they are stationary with respect to each other. That means they are moving with the same speed and they are going in the same direction. So, relative to each other, they are not moving at all. That means they could be moving from one point to another, but the distance between them remains the same. And if the distance between them remains the same, there is no change in magnetic flux. There can be a change in magnetic flux if the magnet was moved closer to the coil or taken away from it. But if they both move with the same speed in the same direction, the distance between them remains the same. And if the distance is same, there is no change in magnetic flux. So in this situation, there will be no induced current. So we know that delta V is 0 only when the magnet and the coil have same speed and they are both moving in the same direction. This criteria must be met for there to be no induced current. So if you look at the four cases here, there is no induced current only in case C. Because in this situation, both the coil and the magnet have the same velocity, the same speed V, and they are both going in the same direction. So when I find delta V for them, I get it as Vc minus Vm, which will be nothing but V minus V, which is 0. And if the relative velocity is 0, that means there is no relative motion between them and there will be no induced current. Now for the other cases, either the velocity values are different or they are going in opposite direction. Like in case A and D, you will notice that the two velocities are in the same direction but their magnitudes are different. So if I find delta V for them, like for case D, I get delta V to be Vc minus Vm, which is 2v minus 3v. That gives me the relative velocity to be negative v. It's negative in value, but it is not 0. Same will be with case A. Relative velocity here will be v by 2 minus 2v. And after solving, I get delta v as negative 3v by 2. Still, it is not 0. And since it is not 0, there will be an induced EMF or an induced current. In case B, the coil and the magnet have the same values of velocity, but they are going in opposite direction. So if I take the direction of coil to be positive, the direction of magnet will be negative. And when you do Vc minus Vm, you get 2V minus minus 2v because they are in opposite direction, hence the negative sign. That gives you the relative velocity to be equal to 4v. So in case A, B and D, the relative velocity is not zero. Hence we say that there is an induced current in these cases. And only in case C, the induced current will be zero as the relative velocity between the coil and the magnet is zero. So I can write my final answer as in A, B and D, there is induced current. And in case C, there is no induced current.